Hi everyone. I welcome everyone to the third lecture of STEM's 2022 final camp. Today, we are delighted to have Professor Prahladh Harsha with us. Let me start with a brief introduction about him. Professor Harsha is a professor at the Tata Institute of Fundamental Research, Mumbai. His research interests are in complexity theory, coding theory, and information theory. He completed his PhD at the prestigious MIT under the guidance of Professor Madhusudan. He is also the recipient of Swarna Jayanti Fellowship Award in 2015 and 16. Today, he will be talking about the extremely fascinating topic of probabilistically checkable proofs that allows us to verify whether a proof is correct or not just by looking at few bits. It also has many applications like in cryptocurrency and blockchain. Before we begin, just a quick instruction. You can put your questions or in the chat, or you raise your hand and the moderators will voice them at the appropriate time. Without further delay, I invite Professor Prahladh Harsha. I hope all of you enjoyed the talk. The stage is all yours, Professor Harsha.
Thanks, Amik, for the generous introduction. I'm excited to be part of this STEM's 2022 program. Good to see all of you. If you guys, some of you be happy, I'll be speaking, as Amik mentioned, I'll be speaking on verification through the computational lens, in which and hopefully convey some of the ideas behind the notion of probabilistically checkable proofs. By the way, I would like this to be an interactive session. So if at any point of time you feel free to stop me and ask questions, both in the chat form or whichever the moderators do. And if some of you could turn on your videos also, if you could turn on, it'd be good, because then I will feel as if I am speaking to people. But of course, it depends on your internet connections. If you could turn on your videos, it'll be good, because then I will have a feel of whom I'm speaking to. Okay, let's get started. So roughly what I plan to do in the talk are the following. I'll be trying to cover the following four things. I'll start off with giving an introduction of what proofs are, what does verification mean, and we'll look at both of this from the computational perspective. Proofs have, of course, always been there in the notion of mathematics since time immemorial, but we'll look at it more from the computational angle. And then once we develop this notion, we'll then go on to discuss what does it mean by asking about super fast verification. And this will lead us to the notion of probabilistically checkable proofs. And we'll spend some time defining this notion and see how it's useful. We will then see some applications of probabilistically checkable proofs based on time permits. And I'll try to give a bird's view point of how such super fast verification is obtained. So let's begin. So we're going to start off with our first thing. What are proofs? What does it mean to verify proofs? So the moment you hear about proofs and verification, one of the most natural examples that comes to one's mind is, of course, this Fermat's last theorem, which was proved 2.5 decades ago. And this all started off with Pierre de Fermat, who in 1637 stated this conjecture that there doesn't exist a set of positive integers x, y, z and n greater than 2 such that x power n plus y power n equals z power n. Of course, when n equal 2, these are the Pythagorean triples, and we knew several civilizations. The Diophantines knew about the solutions for these for n equals 2, but we never knew of solutions from n equals 3 onwards, and Fermat actually conjectured that this is false. He actually not only conjectured, he actually stated in his notes that he had a proof, but his margin was too small to fit the proof. Of course, today we don't believe he had a proof. When would you believe such a statement? Only when people can all make statements, like today's politicians make a lot of statements. You believe them only when they give a proof in support of it. So we'll understand what does it mean to be a statement to be true. They have to give a proof for it. And for this particular thing, in fact, Fermat's last theorem, actually till it was proved about 2.5 decades ago, it actually was into the Guinness Book of Records for one of the mathematical statements which had the most number of unsuccessful proofs. There were several mathematicians who actually gave a lot of false proofs for this. And all of this finally came to an end 3.5 centuries after Fermat had conjectured it due to Andrew Wiles, who published a proof. in 1994. He released a proof. Actually, he did this in a talk in Cambridge University. He released the talk. I don't know if any of you know the story, but back then, the 1994 was almost the same time I was your age. I was in high school, just about to start undergrad. It was a very exciting period. Andrew Wiles had released this fact that that he had a proof, but the math community did not accept it as a proof. There was going a lot of back and forth for a year and a half, in which the mathematicians discussed this whole verify. Is the proof correct? They actually went through this whole verification process. This one, and actually, there was a point of time in which they noticed a bug in the proof, and it felt as if the proof will break and fall apart. And Wiles actually then worked with the student Taylor and actually fixed this proof in the subsequent year. So I remember it was a fairly exciting part in that time when I was an undergrad of all of these happening. So actually, eventually the proof of the Fermat-Last theorem goes in two papers. One is due to Wiles and the other with Wiles and his student Taylor, these two together. So it took a 2-year process for the verification of this proof. So Wiles published the proof of the Fermat-Last theorem as proof. And this is what we would like to understand. We'd like to understand, what does this whole thing mean? That is, you have a statement, say in this case, a deep, profound mathematical statement like Fermat's-Last theorem, or even simpler statements. Ask this, and what we want to ask is, what does it mean? What does it mean? What is a proof? So we'd like to understand, what does it mean to have a proof? And more importantly, even before this, we need to ask, what does it mean? What is it that is being proved? A proof is of something. What is it? What is being proved? So these could be deep mathematical statements like Fermat's-Last theorem, which was proved by Wiles and Taylor and Wiles in 95, or the Poincaré theorem, which was proved by Perelman. If some of you know this, Gregory Perelman in 2003-2004 released the proof of Poincaré theorem. One thing which will not fit in this notion for us is the Riemann hypothesis, which is still a conjecture around, and we don't yet know whether it's a true statement or not. So these are statements of deep mathematical theorems, and you can formalize what a proof means for this. But we'll also be interested in much simpler statements of this ones. For example, what I don't have a better word for it, so I'll call it a shallow statement, because in comparison to these deeper statements from math. For example, somebody could tell you, you play Sudoku, and they say, I know how to win in Sudoku. And what's one notion of a proof? They actually show you the winnings, this ones in it. They mark all this ones and say, this is my winning strategy in it. That's why I know how to solve this Sudoku. Or you could ask, if some of you have seen a bit of computer science, this one you would notion of this graph. You're given a graph, or say a map, a set of a graph which is a set of nodes and vertices, and somebody says this graph is 3-colorable. And what do I mean by that? You can color the vertices of the graph such that every two adjacent vertices receive a different color. Somebody could claim this. That could be a statement. For example, somebody could claim that the graph which consists of the countries of the various world, when you draw the map, they are actually 3-colorable. This is actually not true. You require at least 4 colors sometimes for certain maps to draw it, and it's known that 4 colors are sufficient. So this is a statement. It's a sort of much shallower statement. Somebody could say that this number is prime, for instance, or it's composite. And in this case, a proof of it would be the fact, if it were not prime, a proof of it would be the factorization of the number. So in each of these cases, there's a different notion of a proof, but once we have this proof, we are sort of convinced that the statement is true. We can talk of even more simpler statements, which are more shallower statements, which will actually be useful for us in our context. So in the context in today's world, we sort of delegate storage to huge devices. Like we put in a lot of, most of our things reside on the cloud. We also sort of delegate computation to devices in the cloud. Now, most of this time, we actually believe the computation that happens is correct, and we just take its word for it. You can now question, why is this computation correct? And ask the person whom you have delegated, provide me a proof that what you have done is actually correct. And these are fairly important. For example, I think earlier this year, IIT Kanpur had released, they sort of begun releasing the degree certificates, not only as usual degree certificates, actually release the degree certificates on the blockchain. Now, blockchain is something which is publicly writable by various parties. Now, how do you know that when you read the thing on the blockchain, that's actually a degree certificate of so-and-so person? So I could be an IT degree undergraduate student, and I say this is written there. What prevents me from having written it and said there that is my certificate out there? I don't have an IT Kanpur. I didn't do my undergrad. What prevents me for it? There's a notion of you have to somehow add to it a proof over there. Or if you say you're dealing with Bitcoins and stuff, when you go to a store and you buy something with a Bitcoin, unlike a rupee currency or dollar currency, is not a note or something which you have. It's a digital piece of this one. How do you provide proof that you are actually the owner of the digital coin and you're just not copied your friend's Bitcoin software and you're trying to this one? Each of these you have to have notion of a proof. So let's actually go a little more and try to abstract out this notion of what does it mean to have a proof. And there are two objects over here. There are two parties over here. There's somebody who is providing the proof. In the case of the IIT thing, when the certificate is written, IIT Kanpur is providing the proof somehow over there. And then there's a verifier. The person who wants to check it, he has to check. There are these two notions. There's two parties over here, the prover and the verifier. So let's try to formalize things a little more. So suppose X is the statement that we wish to prove. This could be any of the statement that we wish to prove. This could be an abstraction of this one. I'm going to take a computer science viewpoint. X is just a string of bits for now. This could be Fermat's last theorem. This could be the fact that this particular number is composite. Any one of this, it's just one string, and you want to prove this. And who is the entity that you want to, whom you want to convince? It says it's some verifier. There's some object out here. There's a verifier. In the computer science, this one, typically this will be an algorithm which is trying to check. The verifier will be notion, but for now it's just some object that wants to verify it. And how do you check it? You're going to give this object a proof. This is very bad. You're going to give this object a proof by, which is some sort of long string that the verifier reads this object, and then at the end of it, it's convinced that the object is this one. But what does it mean it's convinced? You must have these true properties. That is, there should be a notion of true statements. So let's call L to be the set of true statements. We want two properties to be satisfied if you want to be convinced. That is, if X is in fact a true statement, there must exist one such proof which convinces the verifier that the statement is true. And similarly, if the statement is false, there must not be any proof pi which convinces the verifier that the statement is true. Only if the verifier has this property, then do you accept this as a valid proof system for this one. You need this verifier, the verification. So verification process should have this. It's not sufficient for me to just have a proof. The verification process should be accompanied with these two properties, which I will refer to as the completeness and soundness properties. What does completeness means? Everything that is correct must have a proof. And soundness says that anything that is incorrect must not have a proof. Of course, this is just a formalism of the way mathematicians have done the proof. Typically, in the case of Fermat's last theorem, the proofs were supposed to be written in some informal mathematical language. The verifiers are a bunch of mathematicians who are checking it out. In the case of this blockchain and Bitcoin, there is the software out there which is checking whether your Bitcoin is valid or not. So that performs the role of the verifier. And the proof is for every Bitcoin, there will be a corresponding long proof stating that why this Bitcoin is actually a valid Bitcoin. So it will be the entire history of the Bitcoin right from the time it has been minted all the way up to now. The history would be written there, and that's proof that this is actually a valid Bitcoin, along with all the digital signatures and stuff. And then there is a piece of software which is verifying it. And all of these softwares, all of them should have these two properties, what I will refer to as the completeness and soundness properties of this proof system. Is that fine?
So there's one
This is all,
question.
I've just generalized things. Now we'll take a more computer science perspective to it. We'll take a computational. We'll add some efficiency requirements to this proof system.
Hello, sir.
Yeah.
Yeah, there's one question that
Sure.
doesn't a counter example suffice to prove that a statement is false?
A counterexample is sufficient to prove the statement is false, but you want the question, that's a proof that the statement is false. That's a proof that the statement is false. When I have a proof system, I'm saying a particular verification process. A verification process states that correct statement should have proofs. False statements might have counterexamples or might have, but must not have proof. There is a particular way of checking. I'm defining the notion of checking whether a statement is true or not. This checking process should have some requirements. When do you trust this checking process? On one hand, it must be the fact that it checks everything that's correct should pass through the check, and anything that's incorrect must not pass through the check. This is a basic requirement of it. Of course, you can tell me proof of showing something is incorrect. That's an extra feature that some things might have counterexamples. For example, tomorrow somebody might come for the Riemann hypothesis and give me a counterexample and say, this is the reason why it's false. But a checker need not have the extra property that it has to produce a counterexample. If it can, well and good. But at the very least, the thing it should do, it should be able to check everything that's correct and reject everything that's incorrect. It could come up with a counterexample for it, but that's not necessary for a checker. So for example, if you come up with a spurious Bitcoin, the software should just at that point say, this is an invalid Bitcoin. It doesn't have to tell me, oh no, you are trying to fake it in this particular way or some such thing. It doesn't have to do any of those sort of things. The basic thing checker you want is just to reject invalid statements and accept all valid statements. Okay, does that answer the question? So what we will do now is add a computer science perspective to this. We will we will expect both the proof and the verifier to be efficient. Otherwise, it doesn't make sense for us to look at this object. We're going to say we will only look at proofs which are polynomially long. What does it mean to be efficient? I'm going to look at proofs which are just polynomially longer than the statement I want to prove. If the proof is too long, then I don't have sufficient time to read this proof. And furthermore, the verification process should also be an efficient process. It should run in time polynomial. Polynomial is just our notion of efficiency. You could work with a different notion of efficiency, in which case you will modify it accordingly. Sometimes they will put as probabilistic polynomial time. You can put as nearly linear time, whatever. But for the purpose of this talk, let's talk about these notions of efficiency. That is, not only do I want this object, this proof, I want this pi to be only polynomially longer in the length of the proof. And furthermore, I want this to be a polynomial time verifier. This doesn't make sense in the terms of math proof statements, but now because I'm going to give a computational angle, these are the type of verifier objects I'm going to be talking about. Okay. And if you've seen what I have done basically right now is the definition of NP. Some of you might have heard about this. This is basically what I have led you to, is this definition of the class NP. So let me just formalize it. NP is a set of statements is said to be in NP if there exists a polynomial time verifier. So the important things are these. If there exists a polynomial time verifier, the key thing is a polynomial time verifier, such that for every statement in the language, or in the language is what is called being true, every statement in the language, there exists a proof which is polynomially sized. That's important over here, which convinces the verifier that the statement is true. In this case, so the verifier accepts. And the other case, soundness, if the string is not in the language, or equivalently, this is stating that X is false, there must not exist any short proof that convinces the verifier. This one, or I think it's better to actually write it this way. For all proofs, this one, it must be the case that this should be 0. That's equivalent to what I had written before. So this should be happen. You should reject every purported proof, and furthermore, the proof should be of every purported proof of polylength. This is exact. So people who have seen the definition of NP, what we have done right now is just, this is the definition of NP. The notion of NP. NP is exactly those set of strings for which you have short proofs of membership, which can be efficiently checked. That's an equivalent way of stating it. So for example, fact that these numbers are composite. This is a language in NP because for every such statement, you can give me a short proof. How I come up with a short proof is a different story. I'm not stating, so in this, notice in this definition, I'm not asking how hard it is to come up with the proof. That's a different object. You require an Andrew Wiles for it or a Gregory Perelman for this or something. I'm not asking how to come up with the proof. If you give, for every such statement, there is a short proof that they can give me in order to convince me the statement is true. Or if the statement is false, no matter however smart you are, you should not be able to come up with a proof that you can fool. You might be the smartest person in the world. You should not be able to come up with a proof that will. This is what NP means. And P is similarly languages in P. This is not how P is usually defined. Language L is in P. If a deterministic polynomial time verifier can come up with the proof, can produce the proof. It's only those statements for which produce the proof by. So that's the difference I'm going to say. NP is sort of, this is not the way P is usually defined. P is usually defined as those problems which can be solved efficiently. I'm saying those problems for which you can come up with the proof yourself by a polynomial time verifier. NP is, I don't care who comes up with this notion of proof, but I must be able to check the proof is correct or not. So NP versus P is basically, if you see, it's trying to do? It's trying to distinguish. P is exactly those problems for which you can produce the proof. That is P is exactly those problems in which proving is easy. NP is those problems for which verifying is easy. I do not know how this one. Certainly one is within the other. If you can prove, you can also verify. So certainly P is contained in NP. That's why this figure looks like this. And the sort of $1 million question, literally $1 million question, is the question, is P a proper subset of NP or not? Or are they problems which it's basically trying to formalize this notion is that verification is easier than proving. This is a statement which we all sort of believe, that if somebody does the calculations for me, I can verify it possibly, and verification is an easier task. And the question whether asking whether NP equals P is basically sort of a computational way of formalizing this statement. Is verification an easier task than proving a statement? Okay, you might have seen this question at various places. This is what the P versus NP question. The P versus NP question is exactly trying to distinguish this notion of proving versus verification. These are two, when you talk about trying to prove statements, there are two parties involved here. One party who's trying to come up with the proof, and the other party who's verifying the proof. P is exactly those things for which even coming up with the proof is easy. NP is those things for which if somebody comes up with a proof, verification is easy. There might be things which are beyond NP and P. There might be things for each. Even proving is hard and even verifying is hard. I'm not going to talk about those things, but about these things, P versus NP talks about exactly these questions. Okay. And what do we know about this? This is in fact, in some sense, this is one of the biggest exports from theoretical computer science to the rest of the scientific community. Today, in today's world, lot of problems. We study various sciences, study various types of problems, and they ask, is this problem easy? Is this problem hard? For example, some people look at multi-body motion in physics, or some in biology, you look at protein folding or this. Are these easy tasks? Are these hard tasks? They do. And several of these have been studied by trying to understand this notion of NP completeness. What is the notion of NP completeness? You look at this set of all problems that we have, all problems in NP. We know that these are all problems which we believe are hard. You ask, is there a hardest problem in NP? And in fact, Cook-Levin in the 70s did show that there is some problem which is called, say, 3-SAT, which is, okay, is there an issue with the recording or?
Oh, I got disconnected. It should be fine now.
Okay, fair enough. Okay, so a whole bunch of there's a problem like this, like say 3-SAT, which is supposed to be, in some sense, what the Cook-Levin statement saying 3-SAT. This is a mathematical statement. What it informally means is the following: is the hardest problem in NP. What it means is, if you can solve 3-SAT, you can solve every problem in NP. 3-SAT seems as if it's a shallow problem, but what you can actually show, it's not just a shallow problem. Even though it's a shallow problem, even these deep math theorems, which are also sitting in NP, will also become easy if 3-SAT is small. And then there was a notion, then there was a whole theory in which there was not just one problem, but several other problems. Like, you might have heard about these problems, like traveling salesperson problem after independent set. Protein folding. Several of these problems were all shown to be also what are called these NP complete problems. A whole bunch of these problems were shown to be. So all of these problems sort of are the hardest problem. Even if you solve one of them, you will solve all of them. And in fact, NP collapses to P. So in several sciences, this is the notion of NP completeness is used to show that a particular problem is hard. They actually show that that particular problem is as hard as 3-SAT. And hence, if you solve it, you're solving all of NP. So we don't believe it's an easily solvable problem. So this is NP. Okay, so it's been going on for a while. So there's this notion, we talked about the notion of proving versus verifying. And the NP versus P questions tries to answer the question of what's the difficulty of proving. And if you really believe NP is not equal to P, then proving is really a more difficult task than verifying. The proving versus verifying task, these are two different tasks. And the NP versus P question goes to the heart of asking what's the difficulty of proving. Now we can turn the question and ask, how easy is verifying? We know verification is easy. But how easy is verifying? We know, for example, if you want to read a particular thing, you just check the whole computation and check it this one. Can you make it even more efficient than that process? That's the question which I am going to address in the rest of the talk. Can verification be made even easier than what it is? So far, the notion of easy for us was there was a polynomial time algorithm that solves the problem. That was what we meant by easy. Now I'm going to ask the question even further and ask, can I make it even more easier than that? And you would ask me, why would you want to do this? Why would you want to ask easy? As long as it's solvable polynomial time algorithm, that's what we mean by easy. We will see some applications why this actually become important later on in the talk. It'll be important to have even super efficient verification. Okay. Questions so far? This comes to the end of my first part, and we'll now moving on to what I'm going to extend this notion of verification to what I will refer to as super efficient or super fast verification. Any questions? No? Let's go ahead with. Yeah?
Yeah, you're good to go.
Okay, let's go ahead. Okay, so let's look at the model again. So we have this one statement X. I want to define one, and I want to prove, I want to ask, can the verification, so there is some statement X. This could be the fact that this graph is 3-colorable. This could be the fact that this number is composite. This could be any one of these statements. And the usual way which we said verification is easy means there is some proof I can give you such that a polynomial time verifier can read the entire proof and be guaranteed of the veracity of the statement. That's what it means to this one. So at the very least, this verifier needs to read the entire proof. He has to run in time at least. He has to read the whole proof. How do you ever check? If I'm verifying whether your homework is correct or not, I need to read the entire homework. Can I check whether the homework is correct without reading all parts of the homework? The question is, what we'll try to show is there is a way in which you can write the homework. What I'm going to say is, we're going to allow the verifier process, the verification process, to have a little more power. We're going to make the verifier a probabilistic verifier right now, so it can toss random coins. So in particular, it can toss coins. You'll ask, what's the point of tossing coins? When I'm checking a proof, I need to be assured, I need to be satisfied. There must be no probability of error. But the reason why I'm going to do this is for the following things. So and I'm going to say the proof can be written in a slightly different fashion. So this same proof is going to be rewritten in a possibly longer fashion. Let's call this capital Pi. This is another proof. Such that the verifier, now previously noticed this verifier only read this. He had to read this entire the verifier had to read this entire proof to check whether the proof is correct or not, which will infer guaranteed to the verifier that the statement is correct. Instead of this probabilistic verifier is going to do the following thing. It's going to toss a few coins, and based on this, it's going to read the proof at just a few locations. Say this location, this location, this location, this location. It's going to read the proof at a few locations, and then just read the proof at some locations. These locations will be random. When the prover writes the proof, he doesn't know which locations the verifier is going to probe the proof in. But the verifier probes only in, say, 4 queries, 4 locations, 4 bits, and is guaranteed. This is what I'm going to talk about as efficient verification. There is a long proof, but yet to check the veracity of the proof, you don't read the entire proof. You only read a constant number of locations of the proof and are yet guaranteed of the success of the veracity of the proof. What does it mean, guarantee? Let's go back to our completeness and soundness statements. We had this statement. We had X previously in the deterministic verifier. This was what completeness meant. If X is in L, then we must have that there exists a proof that B of X pi is 1. We are now going to change it to state that there exists a proof such that this verifier, this probabilistic statement, this verifier, over that when he reads the proof and pi, it's going to accept, it's going to be with probability. So always the verifier should accept if the proof is correct. If the statement is correct, there must exist one proof that no matter which few locations accept. But the interesting part is this one. So out here, what I'm going to write state is the probability that the verifier accepts should be at most half. That's the key. This one, we're going to say it here. So let's stare at this definition a little more. I'm giving the verifier a little more power by making the verifier a randomized verifier object. Unlike previously where it was a deterministic object, it's now a probabilistic verifier. But I'm making the verification very super efficient in the sense that you don't have to read the entire proof. You only read at, say, 10 locations of the proof, 4 locations as this picture says. And yet you should be convinced of the proof. That is, in the S case, there must be one way of writing the proof such that you always accept if the string is in the language, then there's always one proof that causes the verifier to accept. If the string is not in the language, then no matter what you give me, the verifier should not be able to accept with probability greater than half. Notice this is not true. You can ask, is this true of a usual proof that we give? I give you. In a usual proof, I could just give the error. I could just make an error at this one location. That is, I give you a math statement and I give you a proof. I give you an error in this location. If you don't read the entire proof, if you manage to skip, if you check that every step follows from the previous step, but you don't check this particular wrong step, you are not going to realize that the proof is buggy. But whereas here I'm stating that you can read proof only at 4 locations, but most 4 locations will actually find out that there's an error in the proof. You are going to be able to notice that there's an error in the proof no matter where this one. This is what the statement is telling you. So let's write down what are the advantages in this one. So the advantages is the verifier only looks at very few bits, possibly even constant, of the proof. Okay, that's the key advantage. One disadvantage is now the verifier is randomized. So there is a probability of error. Unlike the previous case, if the verifier said accept, it was always correct. Here, there's a small probability of error. This error is half. This half can be made, but the error can be reduced by just repeating the verifier several times. Okay, notion of this. So let's look at this notion again. So this is the picture. This is what is called a probabilistically checkable proof. It's the same notion of a proof, except that now the proof is called probabilistically checkable because the verifier is tossing random coins. It's a probabilistic verifier. And strictly speaking, I should have also added probabilistically. The key thing over here is it's locally checkable. Unlike in the past, that's the important feature. The proof is extremely locally checkable. You check the proof by looking at very few locations, just these few locations of the proof. Okay. Questions at this point. This is what I mean PCP. And what will be the parameters that are interesting for us? So if we let n be the length of the statement that we are trying to prove, the parameters that will be interest for us is the random coins, which is number of random coins the verifier tosses. So this is what I will call R. The number of queries, this is what I'll call Q. And the proof length, this is pi. This will be this one. An amazing theorem that was proved in the early 90s due to several authors, due to culmination of work by several people, is that anything that can be proved in the NP sense, for which also has this sort of efficientification. You don't have to follow what this statement means. This statement informally just means the same thing. Any theorem that has a classical proof, that is a proof which I defined at the beginning of the talk, has another probabilistically checkable proof. That is, you can write another proof for the same statement. I call this is what's called the PCP, that can be checked by looking at only a constant number of bits of the proof. That's what this statement means. It's an amazing theorem that such a thing is true. In other words, I can expect you to submit your homeworks in such a way such that I can just look at 4 locations in the whole answer sheet and be convinced. You do not know which 4 locations because that depends on which random coins I'm going to toss, which you don't know, but I can check. So there's a way in which it says that any way in which you can write a proof, there's another way of writing the proof. This is the other. This tells you that this is another way. There's another way in which such that this happens, such that you have this extra property. That's why you can do this local verification. Questions on this? So it seems like too miraculous to be true, but surprisingly, actually, this magic is true. That is, every proof can be rewritten in such a way such that you can allow for this super efficient verification. Questions?
I think everything is good till now.
Yeah. Okay. So what I will do next, how many minutes more do I have? About
maybe 20-30 minutes, 30 minutes.
Okay, sounds good. So what I will do is, let me shift the order. I will first do some applications of why such a thing is useful, and then get on to give you a bird's eye view of how you can construct such an object. It's not going to be possible to give me full details of the construction. Even in a graduate class, typically this takes about 5 to 6 lectures, but I'll try to give a bird's eye view and show you some of the algebra, the math that goes into proving such a statement. Okay, but let's start with some applications. Now I'm reversing the order. I'll do the applications first and then get to the details. So why are such PCPs useful? So recall the theory of NP completeness when we mentioned it in the beginning of the talk. That was basically to show that various problems were all hard. That is, it started off with showing that some problem called, which we said 3-SAT, was hard. And then that was used to show a bunch of other problems. Say protein folding is hard, traveling salesperson problem is hard, independent set is hard, vertex cover is hard. These are various computational tasks, and we were trying to show some scheduling problem is hard. It was to show that. A consequence of the PCP theorem, which I will not get into this talk. If time permits, I can do it in the question and answer session at the end of the talk, shows that several of these problems which we have shown here, their approximate versions are also equally hard. For example, what's a traveling salesperson problem? A traveling salesperson problem is the following thing. It's basically something which Amazon or Flipkart have to resolve every morning. That is, every morning, the Amazon delivery guy he sees, for example, I'm from Bombay, so he gets the map of Bombay. These are all the locations where he has to drop off things. He gets this list of locations. So he has to, of course, go and visit every single location. He has to drop it off. And he knows the inter-location distances between any 2 locations. He knows the distance. So he has to compute the shortest path so that he can do this most efficiently and fast. He's not going to go from north to south and south to north and this one. He wants to do it as efficiently as possible. So the traveling salesperson problem is basically trying to find the shortest route which connects all the n nodes. This is believed to be a very, very hard problem. We don't know how to solve this efficiently. So there's no way of trying to find the best solution. You can ask, okay, if I can't find the best solutions, can I find a solution which is not too much away from the best? Say it's not the best solutions, but you can guarantee that it is at most 110% the best. It's just 1.1 times the best solution. That you give me a guarantee that it's no worse than the best solution. The best solution possibly takes, say, he has to travel 45 kilometers that day. I guarantee that this algorithm, I can give something which guarantees, which is within 50 kilometers. So you can ask this. This way of PCP theorem shows that even these approximate versions for several of these problems are also all hard. These problems are really, really hard in some sense. Okay, but this is not something I want to go into the talk. The main other thing which I would like to spend time is actually, which has been a more recent thing. This happened from 1990 all the way till today. This is the more interesting application. It started off sort of in the early 2010, it's less than a decade old, is PCPs have been used in blockchains and cryptocurrencies. And if you look at it, it seems the most obvious application for it. So what's a blockchain? A blockchain is you have things up in this one, there is a public ledger. People are writing various things up on the blockchain. And when you read something, you need to verify what is written here is correct or not. Just like in a cryptocurrency, it's written on a blockchain, you need to know how it is right. One way of doing it is you have to give me the whole history of everything. Everything's being written there is correct. It's a long proof. For every single statement that's correct, you have to give me a long proof by that it is correct, which will also be actually also written on the blockchain. Now, the question is, if you're going to be sitting and reading each time you do a transaction, if you're going to be reading this entire history to verify things are correct, you're going to be spending a fair amount of time. Even if the reading was polynomial time, it's polynomial the length of the blockchains are just keep growing as they, over time, they're just going to be becoming longer and longer. So you want to make the verification process super efficient. You want to, even though it might be polynomial, you want the verification process not to depend. That is, the verification process, when you buy a Bitcoin, should not depend on the entire history of the Bitcoin. When you're purchasing something, you don't want to know how many hands this Bitcoin has transferred through. The verification process should not. It should be depend only on a constant amount of time. When you buy an object, you should immediately verify that things are, that the Bitcoin is correct or something. So this is where verification plays such a big role. And in fact, the original Bitcoin doesn't have these features, but there have been subsequent currencies which do use these features. The Zcash and several other cryptocurrencies actually add this extra layer. They use this very super efficient verification in this process. In fact, there is a blockchain overlay called Starkware, which uses, in fact, several of the ideas that I will be talking in the next part of the talk. They've actually, this is how it's sort of trying to check verification that happens on the blockchain, in particular on the Ethereum blockchain. The Starkware is a company which actually does this, and they use these efficient verification offered by PCPs and related models to do this. Okay. Questions? Okay. Now this, let's jump into trying to see how such objects can be constructed. In the remaining 15 minutes or so, this is what I will try to do. I'll take a very toy example and tell you how you can construct such PCPs. Okay, let's get to this one. Okay. So what are these PCPs? It's basically somebody is providing a proof to me of some computation or some theorem or something, and you want to check this long computation in a more efficient fashion. You don't want to read the entire proof, but you want to check the proof by looking at only a few locations of the proof. My question is, how can you rewrite the proof in such a way such that people can check the proof without reading all locations of the proof? That's what is this one. Let's take a very simple task. I want to check the grocery bill. So I buy some n items. I go to grocery, I buy n items. Item 1 is so much, item 2 is so much, item 3, and the nth item I buy this, and I have a total. And this guy gives me a total, and you want to ask, I want to check that this computation is actually a correct computation. Of course, this is an easy problem. You'll ask, why do you want to do this? But I'm giving this as a toy examples. Sometimes this might not be an easy problem, but yet you might want to do this. So how to check that the total computation is correct? The computation of the total number. Of course, the first option is to redo the computation yourself or ask somebody to provide the working of the computation. So one option is, of course, you request the workings of the computation. And go over it. That's fine. They can do this. This is efficient. But on the other process, you have to read the entire computation. If you're going to read this computation, will involve at least going over all the steps. Basically, redoing the addition yourself. It's not efficient the way we wanted it. I want to be able to check that the answer is correct without reading the entire this one. By just looking at 10 locations or 12 locations, I want to be convinced that the answer is correct. So how do we do that? How do we do that? So the question now comes to, how do I rewrite? How do I write the proof? Such that the total computation can be checked super efficiently. What I want to do. So to make the toy problem even simpler, I'm going to, so far then these numbers came as integer numbers. So let's assume they're actually not integers, but actually elements from the field GF2. They are just 0, 1 numbers. And the addition is just bitwise addition. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0. It's GF2 addition. So you have, in particular, I have n bits, x1 to xn, each of which is 0, 1, 0, one of these two. And I want to check that summation xi is this particular number. So let's make the problem even simpler to give an idea of this. Even this one, if you look at it, any standard way of doing it, you have to read the whole thing. There's no way in which I can escape not doing the whole computation. But I'm going to say something right now, which in retrospect will be, it's going to be quite marvelous. Just for notation, let's build for any set S of 1 to n, let xs denote just the summation of those bits that are involved in the set S. Okay, so in particular, x5, xphi will be 0 because it doesn't involve anything. Xi will be just xi itself. Okay, so let's get this equation. What I'm going to now provide as proof is the following. The proof is going to be this exponentially long string, which is xs for all s in n. Of course, you will now ask me, I'm cheating, I'm giving an exponentially long proof. You should give a polynomial proof. We'll come to that later. But I'm going to give you this exponentially long proof. For every possible subset of indices, I'm going to give you the corresponding sum. And now, how do I check the test for total computation? It's going to be this following test. I'm going to pick two subsets, S and T at random. Then set U to be yes symmetric difference T. Then I will query the proof at only at the location. Query the proof at I'll check if xs plus xt equals xu. Notice this should be true. If everybody gave it correctly, xs plus xt should be equal to xu. Just look at it. When the sum adds, only the symmetric difference will be added. Now I needed to check that xn is correctly. This is the first part. The next part is now pick any s at random from R. Check if xn equals xs plus xs complement, that is n minus s. Of course, there's several drawbacks to this proof. This proof is exponentially long. But on the other hand, notice how many places it's actually reading the proof. There's 1 here, 2, 3, 4, 5. It's only reading the proof at 5 locations. I won't have time to prove this, but the amazing thing about this statement is this actually checks if the proof is correct or not. It has all the features of the probabilistically checkable proof that I said before. This is a extremely super fast verification. It comes at a drawback. It comes at the drawback of it's an exponential. It's a drawback. It's an exponential size PCP. It's not a polynomial size PCP. The number of randomness is polynomial. This is instead of what I had promised. I had said earlier it was should be these two. But the key important thing which has achieved is its constant query. You're able to check the proof by only looking at 5 locations. It's not like the usual computation of addition in which you have to go over the entire. That would have taken time at least n. In fact, n log n. Addition it takes this time. This is only 5 bits. This one. And that's the most amazing part of this one. So you can make it, but this is of course coming at a cost. It's coming at a cost of making the proof exponentially longer. Now you can ask, the question now to ask will be, can I obtain constant query and polynomial sized proofs? Polynomial sized proofs. So what I will do in the remaining few minutes is sort of tell you that this idea which I gave here is actually, it's not something we pulled out of the blue. It's actually what's called the Hadamard encoding of a string. And we'll see that there are other encodings which will allow for more efficient ways of writing things. So let's just spend a minute or two. This one, what is this encoding happening here? This is, I'm taking an n-bit string and I'm encoding it by a 2 power n bit string. This is n bits long, and this is 2 power n bits long, because for every possible subset yes, I'm giving the potential sum. So it's an encoding which takes n bits to 2 power n bits. An equivalent way of stating this is I'm restating the same thing. I have n bits here. I'm going to be writing a1z. So suppose I want to encode and the n bit string a1, a2, an. For every possible z1, z1, z2, zn n bits, I'm writing down the string a1, z1 plus a2, z2 plus an, zn. Because whenever z becomes 0, those things are suppressed and you only take those partial sums. This is exactly what the Hadamard, and this is the Hadamard encoding. And the key thing about the Hadamard encoding is it's testable with a few constant queries. If something is a Hadamard encoding or not, you can check whether it's a Hadamard encoding or not with just 3 queries. And this is the test, which is what we use. That is pick one question. So I've given some function f. I want to check if this function is actually a Hadamard encoding. One way of checking it is to pick one n-bit string, pick another n-bit string, take the sum of those two and check if this sum is satisfied. This is what is called the Hadamard test. Notice this test is exactly this test which we said here. The first 3 lines of over here. This test and this test are the same. So you can check that something is a valid Hadamard encoding by just looking at 3 locations. This test has this property, this amazing property. It has the fact that if f is a valid Hadamard encoding, this test will pass with probability 1. If the test is far, so in particular, I can say it's delta far, then the test will reject with probability at least delta. The further away it is, this is a property of this Hadamard encoding that you can get. So the Hadamard encoding had this feature, and it was the key property that we used was it was actually testable with 3 queries. Now the question is, can we get more efficient encoding? It so happens there's something called the Reed-Muller encoding, and that's, do I have how much time? I'll take a few more minutes to say what the Reed-Muller encoding and then conclude the talk. What was the Hadamard encoding? One way of viewing the Hadamard encoding is the following. You can think of this as the coefficients of some linear function. Which linear function? In particular, this linear function. A1, Z1 plus A2, Z2 plus A and Z. It's this linear function. And that's the input, and your this is the evaluation of the linear function on all inputs. You could take the same idea, push it further. You view the string A1 to AN, 0, 1 to the N. I'm going to be quite vague over here. That's this one. You view this now as the coefficients of a degree D a degree D multivariate polynomial. And then the encoding is just going to be, so you view it as some multivariate polynomial P. It's just going to be the evaluation of this multivariate polynomial on all points in the field. So it's the same idea. Previously it was linear, and the only difference between last time and now is I'm becoming the linear to a higher degree polynomial. Evaluations of the degree D polynomial on all inputs. In particular, if you somehow look at this as a table, it looks like this. So there is, let's draw this. Okay. So this is the field that I have. So this is the polynomial. It's some multivariate polynomial. I'm giving the value of the polynomial on all points in the multivariate space. So this is some space f to the m. And I'm evaluating the polynomial everywhere. I need to check. There I checked whether it was a Hadamard encoding. Here I had to check whether it is a low degree. It's an encoding of a degree D polynomial. So there's something called the low degree test, which is the equivalent, which is corresponding to the Hadamard test. For this case, which manages to do this. And so these polynomials actually play a big role. The algebra of polynomials play a big role. You do this low degree test to check it, and that's how the PCP theorem is eventually proved. Polynomials play a big role in this. I will stop with this. I'm willing to go into more construction details of it if people ask me after the talk. So just summarizing, we developed this notion of super efficient verification, which is just the usual notion of verification, but now allowing for probabilistic verifier, which now query the proof only at a few locations Q, at a constant number of locations. And so what did we do? We initially started off with giving a computational lens, say give a new perspective on what proofs mean. This led to this notion of PCPs, which is a new definition of NP, and which is super efficient verification, which has some amazing applications. In particular, in today's world, they have these applications towards super fast verification. One, and they've been originally introduced for applications in theory called hardness of approximations. This, I'll stop with this and take any questions if there
are. Thank you, Professor, for this lovely talk. So I think we have a question by Dhruv Bajwati. Yeah, can you unmute it?
Hello, Professor.
yes.
So I had a doubt about the soundness of the probabilities and the,
yeah, let's go
could you scroll up to the place where you define soundness?
Sure.
The probabilistic verifier?
Yeah, over here.
Yeah. Yes. So in this in the definition, you kept the probability to be at most half. So is there any particular reason for setting it to
half was just an arbitrary number for me. Half was just you repeat the thing twice, so it will go to 1/4. So this half was just an arbitrary. It is some guarantee. You feel you allow so much error, so you put that much. You have to allow error because there's randomness in the picture. Once you allow so much error, then you say how much error you're willing to allow. Say if you could have replaced this half with say 1/100 or 1/1000, or even actually if you repeat it 10 times, if you repeat it 10 times, it will become 1/2/10. If you repeat it 100 times, it will become 1/2/100. And you'll think 100 times repetition is a bad thing, but 100 times repetition, it's a thing, it's a verifier which is reading 10 bits. If you repeat it 100 times, it's reading 1000 bits. It's still super efficient. It's not reading things which are growing with n. So you can make the error arbitrarily low. Half is just, it's an easier number for me to write. I wrote it, but you can make this as small as you want to. You can make it larger.
Okay.
You can make it 1 over larger than the number of atoms in the universe, and it won't cause any issues.
Right. Okay. And another thing, while saying probabilistic, you know what?
Call it the PCPs.
Yes, you mentioned the word locally.
Yeah.
So could you elaborate a bit
So
on that?
what's the key difference between the usual notion of proof checking? The usual notion of proof checking, you needed to read the entire proof. Whereas here you only
Okay, so
check.
it's needed to start from the beginning.
Yeah, you need to read the whole thing. Whereas here you're reading only 4 or 5 or 10 locations. That's fact. The verifier is very, very local. It just reads, it's not local in some spatial or geographic sense. It's not local that way. Local just means it's very few things rather than a lot of things.
I see. So, aren't there any issues if I, if the verifier starts from the middle of the proof because it doesn't know where to start?
No. So the verifier, it's not, notice, unlike this verifier reads the proof from the top to bottom. This verifier is going to read 10 locations, but the 10 locations are going to be determined by the random coins. So one particular random coins might ask you to read it this one, and this one. Another sequence of random coins reads this one, and this one. So you don't get when you write the proof, you don't get to determine which locations you're going to. So he's going to toss some coins, and based on these coins, he's going to look at. So when you go over all the coins, you will be reading all the locations of the proof.
Right.
So it's just a way in which I'm asking you to write a proof in such a way such that if there's an error in this proof could be erroneous just one location. There is no way you can have just one error location. This error will get smeared all over this one. This is the property of this proof. So even if you read only 10 bits, you will see that error. No, even if there was only one error here, this error will get smeared all over, that you will see this error all over the place.
I see. Okay, thank you very much.
It seems magical why this is true, but this is a proper, if you do a little bit of coding theory, I do not know if you're familiar with any sort of error correcting codes. What does a code do? A code is an object which it's an encoding. Every string is encoded to a different string, a larger, longer string, such that two different strings look very, very different. That is, any difference between two strings becomes different all over the place. And that's what this is doing over here. If there is any error in one place, it spreads the errors all over the place.
I see. Okay.
Yeah, it's hard to conceive this at the very first. It's the same notion as coding, what happens in coding theory. Yeah.
Okay, I'll have a look at that then.
So I have one question. So just a clarification. In the grocery computation, you basically you had two steps. First was checking whether the rewriting the proof in Hadamard encoding is correct or not. And the second step is actually checking whether the computation is correct. Is that correct?
Yeah. So the first checking whether the Hadamard encoding was correct or in your language, this is checking if the Hadamard encoding is correct. And this is checking if finally the final answer is correct or not. You might give the Hadamard encoding, but you might give the completely different answer. This is to check if, there are two parts to it. Firstly, you check that the proof written is written in the correct format. Then once you do that, then you go and check if this particular location in the proof is also correct.
Right.
And so most instructions will have these two parts. There will be a part in which you check that the proof is in the correct format, and then it's a subsequent part where you check that the actual computation is also correct, is what the prover claims it to be.
Okay. And maybe just, so I was just thinking, so what are some other type of rewritings? So one is like Hadamard rewriting and another is like degree D polynomial.
Yeah.
So are there any other type of rewritings also?
So what you want is you want this encoding to be locally testable. You want the encoding to be to have the property that you can, the Hadamard encoding has the property that it can be tested with just 3 queries. That's the key feature of Hadamard. It can be tested with just 3 queries. You just look at 3 locations. The Reed-Muller code, which I said, so suppose you want to check that some large object, it's an M-variate object, it's Reed-Muller, it's a low-degree polynomial. One way of checking it is to just pick a random line. Just look at the evaluation of the points along the line. This will, if something is a degree M polynomial, if you restrict it to a particular line, what you have to see is the univariate polynomial along that line, along the variable in that line. So you just check this. The test for Reed-Muller happens to be the fact that you can check if it's a low degree polynomial by just choosing a random line and checking if along the line it's low degree. So you needed, this was the property that helped Reed-Muller code. It was also had this local testing property. So if another code also has a local testing property, it's conceivable that you can use that code to do PCPs. So there's one other code which is called the direct product code, which also has this property. We know how to do it, but it's been so far we only know how to use these 3 codes to construct PCPs. There might be other codes, in which case you'll have to construct. So first thing which you want of a property of this encoding is you want it to be locally testable. You want to check that the format is the correct format by looking at only a few locations. If the code allows for this feature, then you can construct a PCP on it. Then you might be able to construct a PCP on it. We know how to do this in the case of Hadamard PCPs and Hadamard encodings and Reed-Muller encodings.
Okay, thank you. So there's another question by Soham.
Yeah.
Excuse me, sir.
Sure.
Yes. So using PCPs, we've been able to verify things in constant operations, right? But then, but then the computation essentially goes into creating the exponentially large proof list. So aren't we just
no.
shifting
So exponentially large proof was what I gave as a toy example. The proof is not exponentially large; it's actually only polynomially long.
Okay.
It's only polynomial. So if you use Reed-Muller encoding, if you use Hadamard encoding, it's an exponentially long proof. Of course, the person will come, if I'd use Hadamard, people will complain. Just because to make the verifier's task easy, you're asking the prover to do more work. You're asking the prover to now write, instead of a polynomially long proof, you're asking the prover to write an exponentially long proof. This is unreasonable. You can't, just to make the verifier so this one, you can't make the life of the prover so difficult. If you use Reed-Muller encoding, the proof is also just polynomially long.
Okay.
But the prover will have to do some extra work to write this new proof. Yes. Yeah. Now the PCP theorem tells you that there exists a polynomially long proof also, which is testable with constant queries. I gave the Hadamard encoding, which is exponentially long, that I gave it only as a toy example. If you use the low degree polynomial, not the linear polynomial, then you can get whatever, and you can get it to be polynomially long. Yeah.
Sir, I had a question.
Sure.
Yes, sir. So for verifying the Hadamard encoding, do we take any 2 arbitrary sets, or is there a pattern to the sets we take to verify?
It's 2 not arbitrary, 2 random sets. That is important. It's important it was random. This was random. You needed this random over here. Same thing. This was exactly what happened over here. I needed these tests to be random, not arbitrary. So it has to be a random. Among the 2 power n possible sets, you must pick uniformly at random one of them.
And so that is guaranteed to verify whether the entire thing is a Hadamard encoding.
It will not verify that the entire thing. It will verify that the whole string is close to being a Hadamard encoding. It is true. Certainly, you can't expect I look at only 3 bits of a proof and I can be guaranteed. But once it's close to being, so what will happen is this test, the test is of, as Amik asked, the test is of 2 types. One is checking if it's a valid Hadamard encoding, and then checking if the last, whatever is written here is correct. So the first thing checks that whatever is written here is actually close to a Hadamard encoding. That is, for most locations, what is written here is correct. There might be few locations where it is wrong. But notice that over here, when I'm doing the check, I'm once again picking a random yes. So if it was wrong at a lot of places, this test will fail again.
I see. Okay, thank you.
Yeah.
I had one question. So initially you said that there's some problems which are also hard to verify, which are outside NP.
Yes.
So do we expect? So do we have PCPs for those problems also?
No. So certainly, so the PCP theorem, as I stated over here, is it cannot be because of this fact, because the PCP theorem is in NP. So PCP will not capture anything beyond NP. It's not hard to show.
So like what if?
No, you can only make the verification super efficient if it was efficient to begin with.
Okay.
But you can talk about super efficient verification for things which are outside NP. For example, problems which are, for example, what's the problem which is outside NP? As a natural problem is chess. So I ask you, no, actually, let's not give chess. Let's give Go, the game Go. I want to ask, do I have a winning strategy? I give you a position of the board and I ask you if there's a winning strategy for this. This happens to be an experiment. It's a problem which is known to be outside NP. It's exponential time complete. It's p-space complete. It's p-space complete. You can ask if there is a way in which you can do checking for this also. Yes, you can do super efficient checking. Only thing is the proof will be exponentially long. The number of queries will be constant, 10 or 12, but the proof to show you that I have a winning strategy for Go game will be exponentially long. That I won't be able to get around.
So there is a trade-off happening between the number of queries and the proof size.
No. There is no trade-off. I can always make the number of queries to be constant. The proof length will be the old proof length, whatever. If it was polynomial before, it will be polynomial now. If it was exponential before, it will continue, it will be exponential.
Okay.
Just as whatever type of verification you had in the past, I can get the same verification except with a constant number of queries.
Okay.
Yeah.
Okay.
I didn't state it that way, but that's what PCPs allow you to do.
Okay. So if there are no other questions, maybe we can conclude this. If you have any other questions, please feel free to write to us and maybe we will get them answered by the professor. So thank you, Professor Prahladh, Harsha, for this amazing talks on the proofs and verification. And it is quite interesting to see how just rewriting a proof can get a super efficient verification, just constant bits. And a toy example of the grocery computation made it even more clear. So I'm sure the participants have a lot of questions and would like to read more on this. So I would definitely recommend everyone to check out Professor Harsha's webpage, where you can find his courses on PCP and lecture notes. And there are some other references there also. So thank you so much, Professor Prahladh, for making time in your busy schedule to talk to our participants. Thank you once again.
Welcome. It was great seeing all of you. Nice to see young faces.
Thank you. So we will meet again today at 6 p.m. For the talk by Professor Ruta Mehta on fair division of goods. To see you all there. Thank you.